This video is presented to you by Physics for Students.
Okay, so in this particular video what we are going to do is that we are going to cover a couple of topics which would be this. We are going to see the definitions of homomorphism, homeomorphism and isomorphism. We are going to learn what is isomorphism, injective, bijective and surjective functions. We are going to look forward what is homomorphism, what is the difference between homomorphism and homeomorphism. We're going to look forward how do we preserve structures and equations when we perform a homomorphic equation or homomorphism in a group. We are going to see a couple of examples of homomorphism, what is homeomorphism, what are the homeomorphic surfaces, and how we can build homeomorphic surfaces. So these are the couple of topics that we are going to cover in this particular video. First, we would like to go forward back to our particular roots, as you understand that indeed roots are something which we always try to go forward, and it is better that we know our roots. So this term homomorphism is coming from this Greek term, and it is actually an assimilation of two terms, homo, together or jointly, plus this one morphi, which means form, shape or figure. So as learning the roots are equally important, so these Greek terminologies actually gives an idea to you that what is homomorphism, something which is together and something which carries a form or a shape or a figure. So here on the right hand side of your screen you can see that I've just blended a figure which holds hand together, so you can understand this is a symbolical meaning of homomorphism. When we talk of the term homeomorphism, we actually is going back to the roots, that is the Greek one. This is homia or ditto, and with the same morphe it means together, form or shape or figure. So it is something which is like this, which you see on the left hand side of the screen. So homeomorphism is exactly the ditto one, right? So it comes from the Greek terminology. When we come to isomorphism, it is also taken from this Greek term, and it means equal plus morphe, which would be common for both all these three terms, is taking shape, figure and together. Isomorphism is something like this, which you can see on your screen, that the word isomorphism is carrying a reflection, but it still reflects the same word isomorphism. So we just went forward to understand what are the roots and what is homomorphism, which roughly means together, homeo, which is called in English we call it ditto, and isomorphism, which means equal to the figure. These things will come more clear. This is just giving you a basic idea on what are the terminologies and what are their roots. So isomorphism is something which is equal, homomorphism something which denotes together, and homeomorphism is something which is similar. So these are the three terms, and we will see how in mathematics as well as in topology how these terms are used. So the basic idea of creating this video is that though we use these terms very common, iso, homo and homeo, so iso is equal, is not equal to together, is not equal to similar. So all these three terms are used in three different, I would say, contexts, and they carry different meaning. So in the earlier video we have seen that congruency is being replaced by topological invariance, which means things or the properties which do not change remains invariant. So here it is a property preserved under homeomorphism, and we have seen that a torus, how it performs homeomorphism and becomes a coffee cup. So this is just a kind of a quick recap in order to make you understand that we have learned topological invariance, which is a property which is preserved under homeomorphism. We will deal with isomorphism first, so that things become clear, and we can, once we move forward, we will understand how and in what context it is being used. Now in isomorphism, to be specific, the term isomorphism is context dependent. Obviously, we can say two things are isomorphic if they are the same in all the ways that we care about and different in ways which we do not care about. So we can call it as this. Mathematics isomorphism is a structure which preserves mapping between two structures of the same type that can be reversed by an inverse mapping. And on technical terms, we can tell that isomorphism is a bijective morphism, which in general means this. We have a group or a set with elements x1, x2 and x3, and we have this, and each one of them are being mapped, or they are, you can say they are they are in correspondence with each other. So don't worry about this term bijective morphism, what it actually means. These things will more or less become clear. So so this is what, so here you can see at the bottom of the screen, every member of the domain which is on the left hand side is mapped with every single member of the codomain. So this is how isomorphism takes care of it. Let us see in a very graphical way what isomorphism actually means. Now here is a graph which you can see, and I have just named them V1, V2 in order to denote the vertices. Okay, so you can see that these two graphs are isomorphic to each other, only the second graph is rotated in this direction, right? So that is why we can call them as isomorphic. So okay, let us go ahead and things will become much clearer. This is a kind of a visual depiction of the concept of isomorphism. If you take this graph again, so you can understand 2 is a point which is left alone. On the second graph, it is also isomorphic to each other. Now if you take this kind of a figure, right, this one, and we take this one, so are these two figures are also isomorphic to each other, right? Yes, it is. And we denote here isomorphism by this, right? So we can see that the vertices, I have colored them. So this one on the left hand side and the second one at the right hand side corner, they are isomorphic to each other. So it is denoted by this. Now here you see, I would like to tell you, the viewers, that graph isomorphism has certain conditions, okay, which we are not going to cover up in this video because it would be a separate subject called graph isomorphism. So this is just a visual aid to make you understand about the concept of isomorphism, because if we take graph isomorphism, this part, then we need to consider these two graphs, however, are isomorphic to each other. Now if we are considering how these graphs are isomorphic, which I am not going to explain in this video, as I told you, graph isomorphism itself is a different subject. We need to consider, okay, this is how we do G and J prime. Now we are also going to consider this, right? So the number of vertices, the edges, the degree of sequence, the cycle of length, and there is certain thing called sufficient conditions. So here we are not considering these three. This is just a basic idea on the concept of isomorphism. Here you see both graphs have 6 vertices. You can count it out, 9 edges, and the degree is more or less the same, but the second graph has difference in terms of what is called a circuit length. Hence these two graphs are not isomorphic. So you can denote by this cross that G and G prime, which are these two graphs, are not isomorphic to each other. So as I told you, this is a separate subject. Just to give you a visual aid, what do we mean by isomorphism? Now here you see again, although these graphs A and B are isomorphic graph, C is not, because C, I would say, as hard as we try to, we will fail to match between the vertices of A and to those of vertices of C. So we write that although A and B are isomorphic, A and C are not isomorphic to each other. So this is again an example where you see can G1 and G2 are isomorphic, whereas G3 is not isomorphic. So you can check out why it is not. If you know the basics of graph isomorphism, then you can understand what actually it is. So now, till now, what we have done is that we have got a conceptual, intuitive, visual understanding of isomorphism through visual aids like graphs and figures. Now let us try to define it in a precise way. Okay. So what we can do is that we can tell an isomorphism is a correspondence between objects or systems of objects expressing their equality of their structures in some sense. Okay, we can call this as a morphism. Okay, here it is, a relation between objects or systems which expresses the equality of their structure. We can tell it is a morphism of phi, this, right, for which there exists a morphism of this, which is the inverse one, such that this one and this one are both identity morphisms. So this is a kind of a clear idea, if you are trying to define it mathematically, that the inverse, when it is taken by the non-inverse, it actually produces identity morphisms. Okay, so here is a figure. Right, on the left hand side it is a regular chessboard, and on the bottom of your screen you see what is called a New York's, you can call it a skyline. Okay, New York skyline, which represents to that of a chess. So to give a better idea on isomorphism, I have just selected these two figures. So we select two chessboards, right? One, a traditional one, which is right on the left hand side on your top screen, on the top side of the screen, and another which looks like a New York City line, which is at the bottom. Now they look different, but they are both chess sets. When people play chess, as you understand that we are playing the chess with those sets, they are actually playing the game, playing the same game. So chess is chess, as you understand that we are playing the same game. We say that two chess sets are isomorphic, even they look a little bit different. So New York City skyline chess is a little bit different from the traditional one, yet they look the same, right? However, chess is chess, which is most important. So it will be the same game that we will play, with the same opening, with the same mistakes that we make, the same sacrifices and frustrations we have, and the same winning fervor or the winning zest that we have, all of us. Now all chess sets in this world are isomorphic, even if we purchase online chess sets due to this pandemic. So the black king, this one in any set can be matched with the black king in any other set, which I have shown with this black curved arrow, right? And in any other set, but they obey the same rules, like the movement of the kings will always be the same and make the same moves, right? So any game, any set, it is all the same. It can be played on any set. Now although the internal structures of these, I would say, chess sets or whatever you are playing, the atoms, the molecules, the valency, etc., they might change, but actually it doesn't matter, right? So weight molecules are actually meaningless. They vary from object to object, but it hardly matters. So this is a kind of an analogy which I just thought to share with you. My basic idea is to give you a very clear idea on what actually is isomorphism. Now if we go for a strict definition of isomorphism, then we get this: an isomorphism or isomorphic mapping from A to A prime is a one-to-one mapping from the set A to A prime with the properties this. So that's so you can just see through this what actually this means from Ni. I'm starting from 1 and going to Ni with another set Pj, which is going to up to Mj. So thus in every category of algebraic structure, an isomorphism is a homomorphism, which is a bijection. But just a point, an isomorphism of an algebraic system, okay, so yeah, this completes for all alpha 2 in A, all I in this, right? So what I was telling is that in every category of algebraic system, an isomorphism is a homomorphism, which is a bijection. But you must remember, an isomorphism of an algebraic system is called often as automorphism. We are not going to deal into automorphism in this video, but this is a kind of a strict definition, I would say a mathematical definition on what is isomorphism. Now as we go forward with the intuitive approach of isomorphism into the mathematical approach of isomorphism, I have cited few very simple examples of what isomorphism is, and when we say that it preserves structures, those English words, how do they translate in the mathematical world? So for example, we take this and in linear algebra, and we get this, right? So what happens is that this preserves the operation of addition, as you can see, and when I get this actually preserves the scalar multiplication. So what I'm trying to tell is that you see that how do we do? So the preservation of operation addition and the scalar multiplication is there. As we go further, we can further tell this one A0 A1, which is this, and we can do further this. Okay, so both the operations are preserved, this part and this part. I'm not going to explain further because this is just simple linear algebra, so you can see how these two operations are being preserved if we do this operation of matrix. Now if we further generalize to this one, so for example we get this, okay, with the vectors which pointing A0 A1 and A2, and let us take a kind of a quadratic equation, right? We take a quadratic polynomial and we take this right hand side in the blue screen what it is written. So we take this as an example and we just do the traditional, I would say, quadratic addition, right, which is this one. So we do that, and what we see is that this structure and this one, right? So you can check with this, the structure is preserved and the corresponding elements add in the same pattern as on the right hand side screen. You can do this, and the scalar multiplication, which I have mentioned at the bottom as scalar multiplication, also corresponds with this equation. So this is a kind of a nice, I would say, a nice analogy on what actually is isomorphism. And when we apply this scalar and the matrix multiplication and the scalar multiplication, the scalar multiplication and the addition, both of these cases, the scalar multiplication and the addition, the operations are being preserved. Now if I go forward and I just explain the vector space definition of isomorphism, now I would just like to take a note to the viewer that we will come across with certain terms which I am going to explain to you. You might feel that these terms you already know from your basic course in linear algebra, you can just skip it. But however, because I am explaining it as a self-sufficient complete video, I just thought that it is better to explain. So isomorphism between two vector spaces V and W is a map, which is this, and it is a correspondence F, which is an 1-to-1 and on-to, and it preserves the structure, that is V1 V2 is an element of V, and then this actually happens, and so F of RV is equal to RFV. Now as you see, so we can call V is isomorphic to W. So this is I would say a clear-cut definition of vector space. What I'm going to do is that very quickly I'm going to touch base on what is called an on-to and one-to-one relation with a visual aid, I would say a picture, so that it becomes clear. Those people, the viewers who know already, I'm suppose that you all know, you can skip this part. So we get a kind of a group A where we get few, and we get a group B, and we get few gentlemen, right, who are standing over there, and we get lovely women who are placed in this group B. And what do we see? This person is in love with this person is in love with this, and this person is also in love with this woman, maybe something special, and this person is also in love with this woman. So when we get this kind of a figure, or I would say two domain, let us not go into the technical part, let us not call domain or codomain, let us say a group of people and a group of lovely beautiful women. So we call this as an on-to function, or in technical terms we can call it as a surjection or a surjective function. So this is what we call an on-to function. Now if you get the same kind of people standing over here and same woman who are standing over there, and we get something like this man with this woman, and we get this to this, and this man is in love with this woman, and this man is in love with this woman, then one woman is left, and we call it as one-to-one function. Technically it is called an injection or an injective function. further proceeding, if we get the same kind of a group AB with the same men and women, and we get a correspondence where we find every man is in wonderful love and in a nice way they are in love with those women. So we call it as a one-to-one correspondence function, or technically bijective or bijective function. Now just note that one-to-one correspondence should not be confused with one-to-one, which is an injective function. We just explained it earlier. A bijective function is the one which satisfies both the injective one-to-one and the surjective one-to function. So it means every element in the codomain B, there is exactly one element A in the domain A. So we can say it in this way, that every woman is happy and they're in love with every nice gentleman in this pandemic period. So just a note why one-to-one correspondence should not be confused with one-to-one, which is an injective function. Okay, so we come back to the vector space definition. So we will just, as now we know injective and bijective, so what I'm going to do is that we are going to take this one, like the vector space G, this function is isomorphic to the vector space R2. So how we can do actually this? So now, so what we are doing, just to recap, is that now we know injective, bijective and surjective, and we know in isomorphism what is the definition of isomorphic functions and what is isomorphism. We are going to take forward with the vector space equation, and we are going to see that if this is isomorphic, how do we do that? So to check that, first we need to show that the map is a correspondence between the sets, right, underlying spaces. So first we need to prove this, right, only when A equals to B. So what we get is this. You see the cosine, cos and the sine theta. And by definition we know F is this one, A1 A2 equals to B1 B2. Hence we can conclude A1 equals to B1 and A2 equals to B2. Why? Because column vectors are equal when only they have equal components. So we have proved that this one, which implies F A equals to B, and which means F is the one-to-one. So as you see that when I talked about the vector space definition, there are two conditions, rather three conditions. So we have proved just the F is one-to-one, and there are other conditions which needs to be proved, and we are not going to look forward with that. Those people who are in linear algebra can take this equation further, and they can prove the second and the other conditions of vector space or for isomorphism, right? And you can see that this particular vector space is isomorphic. Okay, so we have certain very basic properties of isomorphism. I would just like to show you on a very quick way. So let G and G prime be groups, and they have identities E and E prime, and this one K N this includes this Z, and then it is just a quick glance over. So if this map is there, then we get this as the first one. If this is there, then we get this one, right? So you can just take a note on what are the properties of isomorphism. I'm not going to take further equations in order to prove the isomorphic properties. Just a quick glance on this. If this is one, so AB equals to B only if phi of A, phi of B equals to phi of B, phi of A. We get this, we get this, and we get this. Right. So these are certain important things without which isomorphism or the topic of isomorphism would be incomplete. So I just thought to go through that. So let us quickly summarize before we move to the other topic. So isomorphism is a correspondence between objects expressing the equality of their internal structures. Two simple graphs are isomorphic if, now I am not going to tell you, as you understand, the vertices, the edges, and the conditions, etc. needs to be satisfied. And two groups are isomorphic if they can pair up all the elements from either group in such a way that the elements correspond to the composition of two, itself corresponds to the composition of the elements and corresponding to the two elements. So this is a quick summary before we move to the other areas, what actually is isomorphism. So what we do is that we take it over from here and we are moving into what is called homomorphism. Now, homomorphism is a way of translating one object to another that reflects its underlying structure. Okay. Now, the mathematicians who have been dealing or who were developing the concept of homomorphism noticed that two different objects, they share some kind of an internal structure. Now see, if you take it on a very close note, you understand that all the mathematical translations which I explained in my first video of topology is that we are on the process of generalizing things from special relativity to general relativity, Newtonian mechanics to Einstein relativity, Cartesian geometry to topological structures. So what we are doing is that we are trying to generalizing something. So if we try to generalize something and we get an object, say A, which has some kind of an internal structure which object B or C can also share. So you understand, for the mathematicians and for the physicists, it becomes extremely easy to understand the underlying structures, do equations, morph, whatever. So mathematicians have noticed that they do share some kind of an internal structures. That these different objects are different, but they do share some internal structure. So we can say it in this way, that there is a homomorphism from X to Y, okay, which means is Y is analogous for X in a highly specific way, obviously, because there are methods and conditions which needs to be proved. So if X is equal to Y, I would say homomorphism from X to Y means that Y is an analogy for X in some specific way. Now suppose we let us give an example. So suppose we have a group, say for example G, right, and we have an operation this. I'm not mentioning it as a multiplication. Let us assume in a clear mind that it is an operation. We don't know what this operation is, okay, and another group H which has an operation, right, this, right. So it is a binary operation. We know that the dot and the multiplication. Now suppose we have a map like this, okay, then the phi is homomorphism or homomorphic if and only if this comes true. Right. So just a very quick and a very basic idea, or I would say a very basic concept on what is homomorphism if you're taking two binary operations. So it will become only homomorphic if the second part is being satisfied. Okay. Now here it is the time that has come which would be I would like to show you the difference between homomorphism and homeomorphism. Now here are a few points. If I take homomorphism, it applies to structure preserving maps in some domains, not others. Almost exclusively it is used in algebra and discrete mathematics. It happens between graphs, rings, lattices, a lot of other things, and it preserves some algebraic functions. We are yet to see, but these are the four important, I would say, points which makes homomorphism I would say a unique kind of an operation, right? If I take homeomorphism, then homeomorphism definitely is a continuous function. It is a topological term. This is very important, right? And it has a continuous inverse. So here, okay, let us go forward. I would like to tell you then the final difference. So homomorphism and homeomorphism, you see homeomorphism is something which is, it is a continuous inverse and it applies to topological terms. Now this is just a quick note for a group homomorphism phi. This is the equation. For ring homomorphism we get this, and for vector space homomorphism we get this. Okay, so this is just a quick, those who are into ring theory, they can understand how homeomorphism applies, and vector space homeomorphism, right? Now I would like to draw an attention to the viewers now that each name that we use, homomorphism, homeomorphism, rings, lattices, okay, they can be very confusing and misleading. Each name that we mention here has a significance in terms of structures, preserving map, right? And these are not closely related to each other. I would like to specify again, they are not closely related. Each and every terms requires a careful evaluation. So here is a kind of a brief list of terms and where it is applicable. So groups and group, we apply homomorphism and isomorphism. Rings we apply homomorphism and isomorphism. Vector spaces we apply linear transformation, invertible linear transformation. Topological space we apply continuous map and homeomorphism. For differential manifold, which we have not yet covered, we called it differential map and diffeomorphism. And for Riemannian manifold, conformal map and conformal isometry. So these are very careful evaluations of the terms. These are important, as you understand that if we are trying to interchange these terms into one another, it becomes erroneous. It becomes a problem. So all this, it is not exhaustive. I have just tried to give you an idea on what these things are and how these are applicable to each of these spaces. So manifold, differential and Riemannian, going to topological, groups, vector spaces and rings. Okay, so now we in homomorphism can take place in groups and rings. The general concept we have to understand is morphism. Morphism is preserving map between mathematical structures. Now if you are given two groups, for example G prime and H prime, or we can call it H hash anyway. So a group homomorphism is a map which is this, right? And it and this one. Right, so you can see that how we have used it. So the phi terms comes before and after the map, or before the map for every G1 and G2 is a member of G. So it doesn't matter really. It doesn't matter whether you multiply first and then apply the mapping part, or you apply the mapping part first and then you apply the next part, vice versa. It doesn't matter. What matters is that are we preserving the structure? So by preserving the structure, what we ensure is this: the image of the group G, which is the first group, under the homomorphism, which is the function phi, is always a subgroup of the group H. So this is particularly very important. So that we are creating a image of group G under the homomorphism phi, which is always a subgroup of the group H. So this is a kind of what we mean by preserving structure. However, things will become more clear as we proceed forward. Now we are going to take a very simple proof on proving homomorphism. So we should try to take it forward together, and we will use by using groups because it becomes easier, right? So if we take say for example G equals to R, B group, these are the group of real numbers, right? Under addition, and H the group of 2 by 2 matrix. We will take a 2 by 2 matrix under matrix addition. Okay, this is the function. So under matrix addition, this is homomorphism, or we can say this is homomorphic. Okay, why? Because you see this operation, right? So phi, okay, further into this, right? So phi of G, this mapping, okay, in further into this. So these are the three steps: phi x plus phi y. Now why we are calling it homomorphism? Because this particular set, if we take it, is actually a subgroup of H. So here, if you remember in the previous slide, what I tried to show you is that it needs to create and preserve the structure, and it creates a kind of a subgroup. So this particular set, as you see under matrix addition, is a subgroup. Now if you tell me why it is a subgroup, so let us see if we can explain it further, right? Now a homomorphism may be injective, which we have explained earlier, or surjective, right? So this function is injective if this condition is true, right? Quite clear. And the function is surjective if this condition is true, right? That is quite clear. Now one thing is that an injective map never maps 2 points to the same point. So we have seen what is injective or injective function. So if the group homomorphism phi is injective, right? So we are considering phi to be injective, then no two elements of G are mapped to an element of H. So each element of G is assigned a unique element of H by the function phi. And what I mean to say is this, right? So this is something, it is a kind of a very clear, and I would say a very easy explanation. What do we mean by injective function, and what is meaning by homomorphism? So yes, so we have created copy of G inside H. As you see, there's arrows pointing. So if it is an injective function, it creates a copy of G inside H. Now further, if you take this kind of a matrix, right, where x equals to y, then x obviously equals to y. So this means this part which I have shown, x is a member of the group of R, there's a real number. So copy of the real numbers is inside a 2 by 2 matrix, right? Right. So the earlier example is injective. Now we are trying to show that if phi is surjective. So if phi is surjective, then what is the condition? Every element of H is the image of at least one element of G under the map phi. So this, right? So here what has happened is that the image of G under phi, I mean to say the function of phi, is all inside. So in some way I would say it in some way it means that the group H lives inside the group G. Also it is not a subgroup, but it creates a kind of an image where the group H is living inside the group G. Okay, now all these are good and fair, right, what we have shown mathematically, but can we show a practical example? The viewers might be thinking that, let us see into what is called a practical example. Now let us consider these two sets, P equals to 1 to 3 and Q goes from log 1 to so on, right? So we know that there is a one-to-one mapping between the elements of P and Q, right? So let us define the binary operators, this and this, and now if you get a kind of a figure like this, you see that on the orange I have marked it. So if the star is applied to 2 and 3, it gives 6, right? And plus is applied to log 2 and log 3, it gives 6. And this one, C equals to, right, obviously. So this is a kind of a quick example, like if you're applying both these things, how homomorphism is taking place and how the same operator are yielding the results, but yeah. So this is a kind of a typical example of homomorphism. Now if I talk of some practical examples, so this is one. Multiplication is a homomorphism for each, although I would say it won't strictly match with the mathematicians, but I just try to give you a kind of an example. This is one. And log is obviously, we know, is a homomorphism from multiplication to addition. Log AB equals to log A plus log B. The inverse is also true because the exponential function is a kind of an homomorphism. So this is a quick summary on what we have actually learned. So homomorphism between two algebraic objects is given by this, which preserves the structure of A and B. A bijective homomorphism is also called isomorphism. It cannot be applied to topology. As I was, under the apprehension before explaining this topic, I told that let us come forward. So homomorphism cannot be applied to topology. It applies to groups and rings, algebra, and so on. So we have learned isomorphism, we have learned homomorphism, and we have learned what is the difference between homo and homeo, and why homomorphism cannot be applied to topology. We are not dealing with this why, but it cannot be applied to topology. And we have also learned what is isomorphism with certain examples. Now we come to the last and the final part, right? What is called homeomorphism. Okay, so homeomorphism, it is a term, as we have just seen, that it is used in topology. So if we consider two topological spaces, X and Y, for example, so F, this is the map, is called homeomorphic if the function is not bijective, that we so if the function is not bijective, we cannot call it as an inverse. So let's see the definition. F is called homeomorphic if F and the inverse function of F are both continuous, which means further this, right? So if it's a bijection, F is a continuous, right? So the inverse function is also, so if you're not taking anything inverse function which is not continuous, we cannot talk of homeomorphism, right? Now when we talk about continuous bijection and inverse function, we mean this. I think intuitively, can you understand that when this torus is being taking the shape of a coffee cup to homeomorphism, it is also taking the shape of the cup back to torus. I think we have explained it. I've explained it in the first video of my topology. You can find out the link in the description box. So this is what we mean, right? So we have explained this. So the inverse is also coming true, right? So this one, let us see for examples, the two octagons, or I would say, let us say two polygons, they are homeomorphic to each other. We can take a ellipse and a circle, they are homeomorphic to each other. We can even take a, I would say this, a cube which is homeomorphic to a sphere, right? And the surface of a torus, is not homeomorphic to a sphere. Right. Let us not go in explanation of why it is not. Let us understand that which is homeomorphic and which is not homeomorphic. Now, here are some examples which we would try to build. Now, just a quick note to the viewers. What we are going to show you, or what I am going to show you, this doesn't mean that they are homeomorphic to each other. But what we are trying to go forward and show you is that how these surfaces we can build from one to another. So first one would be building a one-fold whole torus from a pentagon. So here is my pentagon. Now just note, okay, let us first build it, then we will come to the minute observations. So this goes into this. I will tell you how. This goes into this and this builds into this. Right. So what we have done is that, okay, let me just, I'm so sorry. Yeah. So we have identified the edges, labeled A and these are the edges. So, okay, A and C in the direction. Now, directions are important. If you see, let us go back before we show the arrows. This A, if you can see, okay, let us further go back, right? So you see on the left hand side, the A, it is direction to the right. And the second A is going towards the down. So if you go to the second figure, okay, this A and this A which is going towards the right are preserved, right? And then how this C comes in, and there is a hole in the C, right? So A part is clear, B part is there, and this is C. So this is what we called identifying the edges, and you should be very clear about the direction. So this is one example where we have shown that we are making a one-fold whole torus from a pentagon. Now we are going, let us see an example where we make a two-hole torus from a pentagon. So we are going to identify the edges of octagons in pairs as indicated by the labels and arrows here. So here is here is our pentagon, which will make into this, and into this, right? So the figure shows identifying in the directions indicated with these arrows, the edges labeled A and C. After some bending and twisting, which you can understand or you can imagine in your creative mind, after bending, twisting or squishing, makes a cylinder and marked B and D, right? Now, yeah, here is the B and D. Now, if we now identify the directions in the indicated, the edges labeled B and the edges labeled B, after some bending and stretching, it makes a two-fold torus, which is on the extreme right-hand side of the screen. So this is a kind of a surface which we are making from the regular pentagon to the torus. However, this is just an example to show you. Now I have taken this nice, I would say, animation from Joe's Les. You can see the YouTube channel link over here, just to give you an idea, because these are all mathematics points and equations, how we can create an octagon from a two-fold torus. Just sit back and enjoy the animation. Okay, so this is a nice kind of an animation, but Joe's Les, thank you very much for this animation. Now, my daughter actually pointed out this is from some fairy tale, and you can see it is played by the famous Russian composer Peter Tchaikovsky. Okay, so now we can further make this, which is a kind of a sphere, right? So we can fold this left hand over onto the right hand part, the half, and so on, and it is like a, you know, I would say a zipping a purse, and we can then stretch and inflate until we get this part of a sphere. We can also construct a torus from a unit square by using this and then going ahead this and this and this, right? So it is a construction of a torus from a unit square, and just note the points of 1, this 2, and this 2. So you see how this direction really matters, how 1 on the left hand side is still 1 on the cylinder part, and then the 2 which is pointing this is here and is here, and it goes so the direction part is very, very, very important. Okay, so now that we know homeomorphism between two topological spaces is a bijection with the property of this, which is the inverse and the preserves open sets, right? So what we can do is that we can build some homeomorphic surfaces. So how do we do that? Say for example, here is a cube, and this one, and this one. So in this figure, this sphere, which is ultimate result, is homeomorphic to a cube. It is a kind of a, you can say it is a kind of a pumping air into a lumpy, plumpy surface and inflating it until it takes the shape of a sphere or a balloon or something like that. Now, one thing is important is that the surfaces, here it is, these are edges, right? They're very sharp, right? So we can, you know, these edges of the vertices which are sharp, we can smooth it by stretching, or we can, you know, we can smooth it, or we can, you know, whatever the way that we would like to do. So this is a kind of a, you know, very it's kind of an example of creating homeomorphic surface from a cube to a sphere. Okay, so now we already know this torus and a coffee cup. These are homeomorphic. This one, now this is interesting. These are also homeomorphic, right? But this arrow, this one, sorry, on the right hand side, the blue one, which is called a knotted torus. Actually, the torus and this knotted torus is called a trefoil knot. Right, the torus and the trefoil knot are homeomorphic because there is a bicontinuous map between them. Right, there's a bicontinuous map. Now it is impossible to unknot the torus. As you can see in the animation, you cannot really unknot the torus by bending or stretching or squishing, but whatever the way you can. But can we do it in a different way? This is a very, very, I would say, odd one out kind of a thing. So the trefoil knot, which is basically homeomorphic to the torus because it's a kind of a bicontinuous map. But can we unknot it? So let us see right now. So here is our knotted torus. So what we do from the knotted torus, we separate it, right? We separate it, and then we unknot it. You see the unknotting, right, on the first, second, third figure on the right, and then we glue it. Right, and we glue it, right? So we have to just remember that we should be able to join the points on either side of the cut with which we are cutting the surface exactly as they were beforehand, right? It should be exactly as they were beforehand. The whole operation defines homeomorphism between two surfaces. Now, how do we do it? If we kind of zoom this operation, then it looks like this. So you see this first one on the left hand side, right, on the black and white, you see this is the cut, and then this is the separation. Then we unknot it, and then we glue it, right? So this is a kind of you know, how do we really unknot the surfaces of a tied knot and a tied knotted torus, and how do we then glue, and then we bring it back so that it is exactly the surface and the points are the same. So that's it. I think that I have received enough amount of encouragements from viewers. I'm really very thankful to them who really appreciated my topology video first. Now I know this is a little bit lengthy one, but cannot help it. These are very important and detailed concepts of topology or linear algebra, etc. So what we learned is that we learned the definition of isomorphism, homo and homeo, through the Greek literal words and roots. We learned what is isomorphism. We have seen isomorphism through graph, although we have not considered the minute details of graph isomorphism, but I think that we tried to get a kind of an idea. We had defined isomorphism in linear algebra. We have shown sufficient examples through which the operations are preserved: injective, bijective and surjective. Very trivial, very clear. What is homeomorphism? The difference between homomorphism and homeomorphism. The group homomorphism, how it's preserved its structures, the examples of homomorphism, what is homeomorphism, what are the different homeomorphic surfaces, and how we can build the homeomorphic surfaces. So that's it. I think that completes a kind of a video between isomorphism, which is one part, homomorphism, and homomorphism cannot be applied to homeomorphism, and we should not be using those terms interchangeably. That was the main idea of making my video, is that we should not make it interchangeably, because each of them, preserving structures in maps, have a different kind of a connotation and different kind of a meaning. And lastly, what I would like to do is that I would like to thank this particular very, very senior person, Dr. Richard Sott, who is a retired professor of topology from the Institute of Advanced Studies. I don't need to explain what IAS is, where luminaries is like Gödel, Einstein, Oppenheimer was in New Jersey. Dr. Richard has actually helped me to clear a lot of concepts, a lot of ideas, a lot of thoughts through my constant questioning. Is a very senior and a very knowledgeable person, and he is, I can say, is the ultimate guide for topology. So my sincere thanks to you, sir, for helping me out. So that's it. I think that completes, and the topic of my next video would be, is torus homeomorphic to a circle? We will take forward, analyze and see that can we call torus homeomorphic to a circle. Thank you very much for all the subscribers, all the comments, all the views and all the love that you have shared. I will try to keep up to your expectations, delivering good, nice videos on physics, topology and the areas which I can deliver. Thank you very much. Keep safe and stay happy during this pandemic time, and wish you all a very nice weekend ahead. Bye.